Okay, so let's see if we can get this to work. So what I'm going to cover here relatively quickly is this method of assumed forces. I'll do it with this simple example here. This is obviously a statically indeterminate problem. Method of assumed forces is, it's actually, in my opinion, it's a very powerful approach for solving a lot of different problems. It solves statically indeterminate problems very nicely. I think it does it, except for the most simple of problems, it solves it in an easier way than solving the system of equations. It also works nicely in MathCAD, for whatever that's worth. And for complicated problems, it's definitely easier. Um, the only downside is, the initial thought argument that justifies what we're doing is a little bit non-obvious. But once you see it once or twice and you understand what's going on, then it's not an issue anymore. And so it's just like an initial effort. But then after that, it pays back in that you can solve these problems much more easily. That being said, I'm not going to require that you need to be able to do it both ways, as long as you can solve these problems with one of the two methods. So that's why I'm doing this in a video and not necessarily covering it in class. I also have some other videos solving problems by this method as well. Okay, so here's the basic logic, right? So here's our statically indeterminate problem. We've looked at problems very similar to this. So the total elongation, we have two support forces at A and B. Those are unknown. We can only write one equation of equilibrium, sum of forces in the y direction. But we know that the total elongation, the elongation from A relative to B, has to be zero because it has to stay in those fixed supports. So what we're going to do as a bit of a thought experiment is we're going to remove one of the constraints. So I remove that bottom constraint at B. Now it's a statically determinate problem. And in this particular case, the only thing that goes on is you only have load in section AC. And so that stretches a little bit. So there I got the 2 meters plus a little bit of a delta. And then the bottom section, C to B, just rigidly moves along with the elongation of section AC. Now the question is, we need a force on the bottom. That's the support force at B. What would that force, here I have it written as P, what will be that force that will push point B back up to where it was initially, so that the total elongation is zero? Okay. So that question is actually just really a restatement of the compatibility condition. Right, we're solving for that additional unknown. But if we look at it this way, actually, you'll see on the next slide, it's a little bit easier to do the math to solve these problems, okay? So here's how we do it, and now we're going to see the actual assumed forces bit. So here we've got the bottom constraint removed, and now I've replaced it with a force, and I'm assuming the value of that force to be a unitary value. In this case, I'm picking it to be 1 kilonewton. You can actually pick it to be any value, 32.6 newtons, but it makes the math a little bit easier if you just pick a unit value. So I used 1 kilonewton because a kilonewton kind of scales to this, a little bit more closely. You could do 1 newton as well. It doesn't really matter. Okay? So here's this problem, and we're going to break this up into case 1, right, without the bottom force, and then superimposing upon it just the application of the 1 kilonewton force at B. And so you can see the superposition of case 1 and case 2 give you the initial case that we want. Well, both of these are really easy to solve, actually. So let's look at case 1. So if we solve for the elongation at case 1, right, as we mentioned before, it's only section AC where there's an internal force. Section CB, there's no internal force. So section AC, the internal force is a positive 500 newtons. It's a tensile force. And so the total elongation is just that elongation in section AC. So it's 500 newtons times 2 meters over A times E. And for this problem, that's 5,000 kilonewtons. So if you plug that into your calculator or into MathCAD, you'll get an answer of 0.2 millimeters, okay? That's the answer, 0.2 millimeters. So, if there is no bottom support, this will elongate by 0.2 millimeters. All right, now we're going to put the 1 kilonewton force back on there. If we're lucky, maybe the displacement for case 2 will be minus 0.2 millimeters, or like 0.2 millimeters in compression. If that's the case, then, well, we know the force at B really is 1 kilonewton. The problem's done. But, most likely that's not going to be the case. So in this case, with the 1 kilonewton force, we can see that actually the amount that the bar compresses is 1 millimeter. So the total compression from this case is 0.2 minus 0.1, minus 1. So in other words, it actually compresses by 0.8 millimeters. So the 1 kilonewton force is too much. It's too much force. We need it to be less. Well, how much less? Well, I want delta for case 2 to be 0.2 millimeters, or minus 0.2 millimeters. So excuse me for dropping the negative, all right? But okay, so that is actually 1/5 of the displacement we actually got, right? 0.2 is 1/5 of 1. So the force really wants to be 1/5 of what we applied, the 1 kilonewton force. So in other words, 0.2 kilonewtons, or 200 newtons. So here's just basically stating that, right? We want 1/5 of the force in case 2 to get the total displacement to 0. So if we do that scaling, right, it's the displacement in case 1 over the displacement in case 2, which is 0.2. Multiply that by the actual assumed force, and then we get the actual force to satisfy the compatibility condition to be 0.2 kilonewtons, or 200 newtons, all right? So that's actually the support force at B, and then you can solve for the support force at A quite easily just by sum of forces now, because it's 200 newtons up, 500 newtons down. That means there's another 300 newtons acting up at point A to keep it in equilibrium. And that's it, the problem's solved. So, you have to do 2 steps, but there's no solving of simultaneous equations. And actually the solution of both of these cases is pretty easy. Usually this case 1 and the case 2 for the superposition, they're usually really easy because we've reduced forces, and the problem becomes simpler than even the original problem, okay? All right, that is how this works. Like I said, I also have some other videos where I solve this problems using this method, so look at those. And also I have math, MathCAD doesn't do simultaneous equations, so all my MathCAD solutions are using method of assumed force, okay? All right.